Hi everyone, let us continue our discussion of reactions of alcohols. And in previous videos, we had discussed substitutions, SN1 and SN2. Then we discussed eliminations or dehydrations. And now we are on reaction G. This video is pretty full because we're going to discuss oxidation of alcohols and also the reverse, which is the reduction of ketones and aldehydes to make alcohols. Now, reaction G, we're going to call this chromic acid oxidation. It's also known as Jones oxidation. In general chemistry, you learn oxidation as lose electrons, you're oxidized, gained electrons, you're reduced. It's the same idea here in organic chemistry, but we're going to go by looking at the bonds and what bonds are being made or formed. And for an oxidation, let's take, for instance, primary alcohols. You're going to look at this carbon here attached to the oxygen, and this is primary. The reagent for Jones oxidation could be various different reagents. Chromic acid technically is this molecule right here, H2CrO4. And what we're going to do is we're going to oxidize that carbon to the carboxylic acid. Okay, so what you could remember is that primary alcohols can be oxidized to the carboxylic acid. Now I mentioned in organic chemistry, we're going to think of oxidations in terms of the bonds formed and made. So an oxidation in organic chemistry is you're going to add more bonds to oxygen or add carbon-oxygen bonds. In this case, we went from a primary alcohol to a carboxylic acid. Technically, we went from one carbon-oxygen bond, to 3, because we're going to count the double bond as 2 bonds to oxygen. Yeah. Another way you can think about oxidation is you reduce or you lower the number of carbon-hydrogen bonds. So you minus or subtract CH bonds. Take a look at this carbon here. It has 2 bonds to hydrogen. Now that carbon has 0 bonds to hydrogen. Okay. What's more important, not necessarily the definition or how we're going to recognize oxidation, but what you oxidize to. You oxidize a primary alcohol to a carboxylic acid using Jones oxidation. Now, we're going to come back to this idea of adding more bonds to oxygen, because here we went from 1 to 3. Those of you who are a little bit inquisitive, you may ask yourself, well, what happened to 2? Why can't we stop at 2? That's a special reagent that we'll take a look at later. Let's go to the secondary alcohol. Another way you can see Jones oxidation is, and this is what I typically use, potassium chromate, K2Cr2O7 in sulfuric acid. Uh-oh. Okay, sulfuric acid. Take a look at our example here, and it looks like from the line structure we added as many bonds to oxygen as possible. and we remove 2 hydrogens. But if you take a look at this ketone, it only has 1 hydrogen. So we could remove that 1 hydrogen and create the ketone. Did I say ketone? Secondary alcohol. Okay, so you can start planning. How are you going to make your study sheet? How are you going to make your note cards? Well, I like those two next to each other, primary alcohol and secondary alcohol. We form 2 different products, but you notice that if you think about adding more bonds to oxygen from this carbon, we can't because there's no hydrogen to replace. We're not going to chop off this methyl group. Okay, you are able to remove hydrogen. I'm not going to go through the mechanism in this video. My purpose for this video is to show you the complementarity of these 2 sets of reactions, oxidations and reductions. Okay. What about tertiary? Another way that we could show Jones oxidation is just plainly CrO3. Okay, so on the screen we have 3 ways to represent chromic acid oxidation. Any of those 3 ways is perfectly fine with me. No reaction for this one. Because if we look at the dot, there's no hydrogen to replace with an oxygen or to a bond to oxygen. You could remember that tertiary alcohols don't oxidize under normal conditions, under these chromic acid oxidation conditions. Okay? So if we could get this onto one screen, hopefully, primary, secondary, and at the bottom, tertiary, and those are your products. Okay? I do want to mention that if we take a look at this oxidation here, where we go from 1 bond to 3 bonds, carbon-oxygen bonds, we skipped over the 2. What that tells me is that when we made the molecule that had 2 bonds to oxygen, this is still pretty reactive, and you will further oxidize it all the way to the carboxylic acid. And that's normally what goes in my head. I say all the way. You oxidize all the way. Okay. What that tells me is that the intermediate, the one molecule that has 2 bonds to oxygen, is still oxidizable to make the carboxylic acid. Can you envision what that molecule is? 2 bonds to oxygen? It's this one right here. Let's take this same primary alcohol, and I'll draw you the intermediate molecule. H2CrO4. Okay. This is intentionally in brackets because you cannot isolate this when you react the primary alcohol with chromic acid. You cannot isolate the aldehyde in this case, because the aldehyde would further oxidize to our product that we would predict, the carboxylic acid. And that's what we predicted up here, right? Carboxylic acid. Let me focus this a little bit better. Wrong direction. I hope I can focus this. Ah, there we go, much better. Or a little bit better. Okay, then why do I mention this? Because we can oxidize aldehydes using chromic acid oxidation. So this was just a side note, but maybe on an exam you might see this. CHO. Another way we could do chromic acid oxidation is instead of potassium chromate, we could use sodium chromate. And H2SO4. Okay. You have to recognize that this is an aldehyde, and if you want to redraw it, you can. CHO group is this. Okay, 4 carbons. You should know there's this dot here can be oxidized from 2 carbon-oxygen bonds to 3. Just copy your carbon skeleton, get rid of that hydrogen, and we get the carboxylic acid that we expect. So this is a case where you go from an aldehyde to the carboxylic acid. But again, that was really, we should have understood that by the fact that we did not stop at the aldehyde on our way to 3 bonds to 3 carbon-oxygen bonds of the carboxylic acid. All right, that is page 1, reaction G. Okay, and I think for your note card or your flashcard, maybe these first 3, primary alcohol, secondary alcohol, and tertiary alcohol, to give you your products. And just know that if you're given an aldehyde, that could also be oxidized to the carboxylic acid using chromic acid oxidation. Reaction H. Okay, reaction H is, well, how do I stop here? How do I stop at the aldehyde if I want the aldehyde from a primary alcohol? Do you see how it's very important now? Things are going to be a lot easier if you can state the class of molecules, because now you could remember primary alcohol oxidizes to carboxylic acid. Secondary alcohol oxidizes to ketone. Tertiary alcohol doesn't oxidize. All under these chromic acid oxidations. But I want to know, what if I do have a primary alcohol and I want to stop here? I can't use this reagent because it will continue reacting. It will continue oxidizing. That is reaction H. Reaction H is a special reagent that stops the oxidation of primary alcohols at the aldehyde. Reaction H. Okay. This is called PCC oxidation. Pyridinium chlorochromate. So this is a chromate reagent, PCC. You won't have to memorize the structure, and when you do a synthesis, all you have to do is write PCC. Okay. There are other reagents, derivatives of PCC that you may see, but I only typically use PCC, and it's weakened. Chemists were able to add stuff around the chrome, uh, chromium atom to weaken it so it doesn't oxidize all the way to the carboxylic acid. Let me show you how we can use that to our advantage. Let's take this primary alcohol here, PCC. Identify the carbon you're oxidizing. It's the one next to the oxygen. And now instead of going to 3 bonds to oxygen, we're only going to go to 2 bonds to oxygen. And the easiest thing to do is to just draw your double bond to oxygen. I like to draw the hydrogen on an aldehyde. You don't have to, right? That's a perfectly fine line structure. Okay. Primary alcohol. If you want to stop at the aldehyde, just use PCC. Oops. Okay. Can PCC oxidize secondary alcohols? Yes, they can. If you use PCC on a secondary alcohol, you will still oxidize it to the ketone. Go ahead and test yourself. Pause the video and draw me the ketone of this reaction. Okay, the ketone is this. Okay. You know what I just realized? I don't think I formally, in this unit told you what an aldehyde and ketone is. Although, if you go through the videos for Organic Chemistry 1, we did go through classes of molecules, and we did go through what a aldehyde and ketone are. I could do that real quickly here, but you should review your notes from Organic 1. An aldehyde is a molecule that has what's called a carbonyl group and at least one hydrogen off of that carbon. So this is an aldehyde, and then the smallest aldehyde actually has 2 hydrogens off that carbon. And those of you who are going to the medical field, this is formaldehyde, the tissue preservative. Okay. For a ketone, you don't have a hydrogen off of that carbon. So you have the carbonyl carbon, and you have a carbon on the left and a carbon on the right. That's a ketone. The reactions of aldehydes and ketones are going to be mostly in Unit 2. Okay, but I do want to introduce it here because we're in Unit 1, reactions of alcohols, and you can oxidize those alcohols into your aldehydes and ketones. And if it's primary, you could oxidize it to the carboxylic acid. Okay. That's it for oxidations. We have Jones oxidation and we have PCC. There are several others in your textbook, but I'm not going to go through those. These are the ones that I mainly use in the lab. Let's do the opposite, okay? The opposite is reduction. And reduction, we can think of it as add more CH bonds by most likely removing bonds to oxygen. But we'll see other examples where we don't even have oxygen, where we consider it a reduction. And actually, let's do a little review. And this is going to be very important for our next reaction I. But the review that I want to look at is this. Let's say we have a alkene, but also, why don't we put an alkyne? Okay, how about that molecule? Remember when we hydrogenated it, H2, and you could use platinum, palladium, or nickel? When we verbalize this reaction, we say we reduce the double bond to a single bond, and we reduce the triple bond to a single bond. And literally, we are adding more carbon-hydrogen bonds. Now, the hard part about this particular example is that we got to make sure that we have the right number of carbons. So I'm marking all the carbons that are part of the multiple bonds as dots. I see those 2 dots. And this one over here simply is that. Okay, that is a reduction. And verbally, I say we reduced the double bond to a single bond and the triple bond to a single bond. See, it has nothing to do here with oxygen, but it does add more CH bonds. So in the next reaction, we are going to add more CH bonds. But before we look at that, let me just orient everyone again as to what we're planning to do. In reaction G, the first reaction that we looked at today, we were able to take a secondary alcohol and oxidize it to a ketone. And we could represent oxidation with O in brackets. Now, on an exam, you have to actually put the reagent, either the Jones reagent or PCC, right? We could do it 2 ways, using chromic acid or a surrogate of chromic acid to the ketone, or PCC to the ketone. Either one works. It doesn't matter to me which one you want to use. The last couple of reactions that we're going to talk about in this video, though, go the reverse direction, like this. I'm trying to figure out how to represent this. So that's oxidation. But that O really stands for the oxygen that's being added. I think most people, when they abbreviate reduction, they use H because we're adding more bonds to hydrogen going in the reverse direction. All right, so one is oxidation, going backwards is reduction. Okay. Let me show you our first reduction. And I say first because we have several. We're going to look at selective reductions. How can we pick and choose what to reduce? Because right now on your screen, I'm promising that we can reduce a carbon-carbon double bond, but here I'm also promising that we can reduce a carbon-oxygen double bond. If you have a molecule that has both, are there ways to select for one and not the other? The first reaction is not selective. We're going to reduce everything, okay? And this is reaction I. This is hydrogenation. We've seen this before. Again, we're not going to go through mechanisms in this video. The purpose of this is to have one video that compares oxidation and reductions with these molecules. Hydrogenation of a ketone. Oh, let me put that actually. Hydrogenation of ketones and aldehydes. Because we're not going to reduce carboxylic acids. That's a different unit. Okay? That's a little bit harder to reduce. We're going to reduce aldehydes and ketones, or ketones and aldehydes. Hydrogenation, is H2PT. And what are we going to do? We're going to go back to the alcohol, OH. Okay. Ketone to alcohol. Can also use not only platinum, but you could also use palladium or nickel. Okay. Now, we know from a previous unit, the alkene unit, that we could reduce double bonds. I told you that this reaction is not selective. So if we have an aldehyde, okay, we're still going to make that an OH. We're still going to make it a hydroxyl. But what if I also have a ketone, not a ketone, an alkene right there? You have to reduce both if you're going to use hydrogenation. Let's use nickel, okay? And you reduce both the carbon-carbon double bond and the carbon-oxygen double bond. Okay, now I don't draw the H here because, well, if you draw the H here, you have to draw the second H as well. This is a primary alcohol, right? I like to draw the H's off of the aldehydes though. Locate where your dot is. That dot is on the last carbon. I do this just to make sure that I have the right number of carbons in my product. Okay. So hydrogenation is not selective. You're going to reduce all the double bonds, regardless of whether it's a carbon-carbon double bond or a carbon-oxygen double bond. Okay. Again, we're not reducing carboxylic acids. That is a little bit harder. We're only reducing ketones and aldehydes. Let me show you now how to reduce selectively. We're going to target at first the carbon-carbon double bond. This is reaction J. Reduce alkene, not aldehyde or ketone, or carbonyl, but let me say ketone first. Ketone or aldehyde. Okay, so that's a cool trick, because if we do hydrogenation with nickel, platinum, or palladium, all the double bonds get reduced. Let us pick that alkene aldehyde that we had on the previous example. The reagent is actually very similar. It's going to be H2 again. So it is a type of hydrogenation, but we are going to use a different catalyst. We're going to use rhodium, Rh, rhodium, and typically they call it rhodium on carbon or rhodium on charcoal. It's just rhodium that is adhering to a surface of charcoal powder. Okay, this is selective. We are going to reduce the alkene, but not the ketone or aldehyde. We're going to reduce the alkene, but not the ketone or aldehyde. Let me double check the number of carbons. Okay, selective. Alright, so I'm done with that. How do we do the opposite? How do we reduce the carbonyl group, but not the carbon-carbon double bond? We're going to use what's called hydride reductions. And the hydride, again, is H negative. Okay. Let's take the same molecule. This is a good test molecule because this will show us whether it's selective or not. Again, that could be an aldehyde or ketone. The reagents are a little bit tricky to memorize at first. Lithium, aluminum hydride. And we are going to have that in reaction 1, and reaction 2 is going to be water. You do want to keep these separate, but both reagents are important in the reaction. Okay. And we get this. Look at the opposite. Take a look at this molecule up here. We reduced the carbon-carbon double bond, but not the carbon-oxygen double bond. For this one, we're doing the opposite. We are keeping the carbon-carbon double bond, and we are reducing the carbon-oxygen double bond. Okay. Now, there are other hydride reductions, or other reagents to do hydride reductions. Let me put that here. Sodium borohydride, and the second step, water. Now, sodium borohydride is a little less volatile. We have to keep these two separate because lithium aluminum hydride with water can create a fire. But sodium borohydride is a little bit less volatile, so you can keep them together if you want. And I know I do a lab with my class. I use not water, but I use methanol. But in this case, everything's in the pool. Everyone jumps in the pool. Okay, so that's the hydride reduction. We'll talk more about this for sure later when we talk about reductions of other molecules, especially using lithium aluminum hydride, because that's pretty powerful. But it's not powerful enough to get rid of this carbon-carbon double bond. So take a look at your screen. Both of these are considered selective. Okay. So I will leave you with a at-home problem. Okay. Definitely pause the video once I'm done showing you this problem. If I want to reduce only the carbon-carbon double bond, how do I do this? Your question mark is right here. If I want to reduce both, and if I only want to reduce the carbon-oxygen double bond, you look through your notes, look through the textbook. I want to keep that, and I want to get rid of this. Look through the video again, rewatch the video, and see if you could fill in your 3 arrows. Another arrow that you may want to try is, how do I make this? from the alcohol. Okay. Go ahead and do that at home. Uh, all the information you need to fill in these pink arrows are on this video in these 1, 2, 3, 4, 5 reactions. Okay. All right, good luck.